Welcome to Shanti-Peace for Mathematics. In this video, we are going to discuss about the Cauchy's root test, which is also known as a root test. If you have a series of positive terms and a limit of nth root of an is L as n tends to infinity, then the following statement is true. These statements are same as the D'Alembert ratio test, which says that if limit of this L, the value of L is between 0 and 1, then the summation of an is convergent. If the value of L is bigger than 1, then the summation of an is divergent. And if L is equal to 1, then the test fails. Let us try to prove this statement and then we'll solve a couple of examples which related to this root test. To discuss the proof, we will use the definition of limit. We have given that a limit of an power 1 upon n, that is nth root of an, is L as n tends to infinity. If I use the definition of limit, then what we can say is for every given epsilon greater than 0, there exists n0 belongs to n such that mod of an power 1 upon n minus L is less than epsilon for every n greater than or equal to n0. Now this statement I can also rewrite as minus epsilon by expanding this modulus. We'll write as an power 1 upon n minus L is between minus epsilon to plus epsilon for every n greater than or equal to n0. If I add L in this inequality, then we'll have L minus epsilon an power 1 upon n is less than L plus epsilon for every n greater than or equal to n0. We call it this inequality as 1. Now, for the case 1, we'll discuss the case 1 in which says that the value of L is between 0 and 1. Now, since the value of L is between 0 and 1 and the property of real number, we can say that let us select a positive number epsilon such that L plus epsilon is less than 1. Let us consider this L plus epsilon as alpha and the value of alpha is less than 1 we have here. Now using the inequality 1 we have, so I will use this inequality 1 and in that we will use this part. This is the value of alpha, that is L plus epsilon. This statement is true for any given epsilon. So in particular I am choosing this value of epsilon, and so that we will have an power 1 upon n is less than L plus epsilon for every n greater than or equal to n0. If I take the power n both sides and this value is alpha, so that's why we have an is less than alpha power n for every n greater than or equal to n0. Now we'll apply the comparison test here. If I can prove that this series, that is I can see that it is a geometric series, summation of alpha raised to n is convergent, then by comparison test an is also convergent. And this is convergent because the value of alpha which is less than 1, which is a common ratio in that geometric series. So that's 4 we can write here, but since the summation of alpha raised to n is a convergent geometric series with common ratio alpha which is less than 1, therefore by comparison test the series summation of an is convergent. Now case number 2, in that if the value of L is greater than 1. Now since the value of L is greater than 1, we can choose some epsilon by property of real number such that L minus epsilon is also less than 1. So let us select epsilon greater than 0 such that L minus epsilon is also greater than 1. Let us choose this L minus epsilon as beta, and this beta value is greater than 1. Again by applying the inequality 1, but in this case we'll use this side of inequality. using inequality 1, we get mod of an power 1 upon n is greater than L minus epsilon for every n greater than or equal to n1, because it might happen that for this epsilon which we have choose from the different than the case 1, we'll have different n0. So that's why I'm just saying it is n1, where n1 is some positive integer. And if I take the power n both sides, then this will gives me an is greater than L minus epsilon power n, and this is nothing but the beta power n for every n greater than or equal to n1. Now this summation of beta power n is a divergent geometric series because of common ratio is beta and beta is greater than 1, and therefore by comparison test, so this is a divergent series, so its bigger series is also divergent. So by comparison test we say that summation of an is also divergent. So but since summation of beta power n is a divergent geometric series with common ratio beta which is greater than 1, therefore by comparison test the series summation an is divergent. Now in the case 3 we'll have L is equal to 1, and in that we'll have proved that the test will be failed if L is equal to 1. That means I need to produce a 2 example in which one example gives you the value of L, that is limit of an power 1 upon n is 1 as n tends to infinity, but the series is convergent. And in another example that limit an power 1 upon n as n tends to infinity is 1, but in that case the limit is divergent. So let us case sub case 1. In that let us consider the series summation of 1 upon n. So here we have an is equal to 1 by n. So therefore L is equal to limit of an power 1 upon n as n tends to infinity, which will gives me limit of n tends to infinity 1 by n power 1 upon n, because the value of an is 1 by n. Here it is 0 power 0, so it is an indeterminate form of a 0 power 0. So if you want to find out the limit, you have to apply the log both sides. So that's why it is log of L is equal to limit of 1 by n log of 1 by n as n tends to infinity, and the limit of log 1 by n upon n, and as you know that the log of 1 by n as n tends to infinity is tending to infinity because log 0 is tends to infinity. So this is infinity upon infinity form. This is again an indeterminate form. To find out what will be the answer for this, you have to apply the L'Hospital rule. So limit of the derivative of the numerator, that is a derivative of log, we know it is 1 by 1 upon 1 upon n, and the derivative of 1 upon n is minus 1 upon n square, and the denominator you have it is n, so derivative of n will gives me 1 as n tends to infinity. And if you simplify this quantity, this will n tends to infinity, this is denominators go into the numerator, so that's why it is n upon n square with minus sign, and n will get cancelled out, so it is 1 upon n, and as n tends to infinity 1 upon n will tends to 0, so that's why this will tends to 0. So hence we have a log L is 0, which implies that L is e power 0, which will implies L is equal to 1. So therefore here the limit is 1, but the summation of 1 upon n is divergent as p test, as the value of p is equal to 1 here. Now sub case B, consider the series summation of 1 upon n square. Here we have an is 1 upon n square. We'll need to see what will be the value of L here. So for that let us consider L is equal to limit of an power 1 upon n as n tends to infinity, but the value of an is 1 upon n square, it is 1 upon n square power 1 upon n as n tends to infinity. Here again you just observe that this is 0 power 0, so it is a indeterminate form of the 0 power 0, so therefore you have to find out the limit you have to apply the log. So you have log of L is equal to limit of log of 1 by n square, and this 1 upon n will goes in the front and as n tends to infinity. This is, you just observe that this is n tends to infinity log of 0 upon n, which is infinity. So this is infinity upon infinity form. So you have to apply the L'Hospital rule for this. So that's why this will gives me limit. The derivative of log 1 upon n will be 1 upon n square into the derivative of 1 upon n square is minus 2 upon n cube upon the derivative of n with respect to n will be gives me 1 as n tends to infinity. If you simplify this, this will gives me n tends to infinity n square minus 2 will be there because 2 minus 2 is already there. This denominator goes in the numerator, so it is n square will be in the numerator and the denominator you have n cube. This n square will cancel out, this one n is left in the denominator, and as n tends to infinity this will gives me 0. So that means we have log of L will be 0, which implies that log of L is equal to e power 0, so that will gives me 1. So here is also the limit is 1, but the series, the summation of 1 upon n square is convergent by p test as the value of p is equal to 2, which is greater than 1. So therefore by subcase 1 or subcase A and subcase B, we say that the value of L is 1, but one series is divergent, another one is convergent. So therefore by subcase A and B, we can say that if L is equal to 1, then the test is failed. That means we cannot predict that what will be the output. This will complete the proof of this theorem. Let us solve a couple of examples to check whether the given series is convergent or divergent. So this is example. Test the convergence of the series summation 1 plus 1 by square root of n power minus n raised to 3 by 2. Now here an is this 1 plus 1 by square root of n raised to minus n raised to 3 by 2. That I can rewrite as 1 upon 1 plus square root of root n raised to 3 by 2. Now this is in power, so we need to see what is the nth root of that. So that's why it is, let us see what is the limit of an power 1 upon n as n tends to infinity. That will be limit of n tends to infinity 1 upon 1 plus 1 upon square root of n power n raised to 3 by 2 and whole power 1 by n is there. As you can just observe that this n raised to 3 by 2 will cancel with this 1 by n. So 1 n is cancelled out, so it will left with n raised to 1 plus 1 by root n raised to root n. As I told you, this is a very well known series of 1 plus 1 by x raised to x. As x tends to infinity, this will be infinitive. So this is very well known series that we have. So instead of x, we have here it is e. So you just observe that this is nothing but the 1 upon e, because 1 plus instead of this x we have a square root of n. So that's why it is 1 upon e, and which is less than 1. So by root test, what we can say that the given series is convergent. Therefore by root test, we say that the summation of 1 plus 1 upon root n raised to minus n raised to 3 by 2 is convergent. Let us solve a second example. So test the convergence of the series summation n upon e power minus n running from 1 to infinity. Here the value of an is n upon e power minus n. So let us take the nth root of this, that is, let us see what will be the limit of an power 1 upon n as n tends to infinity. So that is limit of an, that is n upon e power minus n raised to 1 by n is there as n tends to infinity. So that will gives me limit of n tends to infinity n power 1 upon e power minus 1. E power minus 1 will gives me e which is independent of n, so will write outside this limit n tends to infinity n power 1 upon n is there. Now to calculate the limit of n power 1 upon n, this is infinitive power 0 is there. So it is again an indeterminate form, infinitive power 0. So I will calculate this limit in separately. Let us say that limit is capital A is equal to limit of n tends to infinity n power 1 upon n. So to do this one, we'll apply the log both sides. So that will imply the log of A is equal to limit 1 by n log n as n tends to infinity. And you just observe that this we can rewrite as log L is equal to log of A equal to limit of log of n upon n as n tends to infinity. This is, you just observe that this is log infinitive, which is infinitive. Denominator is also infinitive. So it is infinitive upon infinitive indeterminate forms. So we can apply the L'Hospital rule here. So limit of n tends to infinitive, the derivative of log n is 1 by n, and the derivative of n is gives me 1. So that's why this will be as n tends to infinity 1 upon n tends to 0. So that will gives me 0. So therefore the log of a is 0, which implies that a is equal to e power 0 will gives me 1. So therefore the limit of n tends to infinity a n power 1 upon n will be limit of n tends to infinity. E is there, already we have e here, and the limit of this n power 1 upon n we have calculated as 1, so it is e, which is bigger than 1. So that's why we can say that the given series is divergent. So therefore the series summation n upon e power minus n is divergent by a root test. So I will give you this example to homework. You can try for this example. Summation n plus square root of n raised to n upon 3 raised to n into n power n plus 1 as n running from 1 to infinity. So try for this example, check whether this given series is convergent or divergent. The hint is a root test. Thank you very much for listening me. If you like this video, please press the like button. If you have any comments, suggestion or question, please drop down in a comment box below. See you in next video. Till then, bye bye, sayonara.